Hi, my name is Jack Stoltz, and this is my lab report for Lab 4 Magnetic Braking with Faraday. The purpose of this lab was to collect data on a magnet falling through an aluminum tube in order to observe and apply Faraday's law. The fundamentals of this lab were these equations. The results were that the experimental time was about 1.25 seconds, and the computational time for the model was 1.118 seconds. Models and assumptions for the models: the magnet was used to model a magnetic dipole with an aluminum foil magnet, modeled a tube through which it fell. The assumptions: we assume that air resistance acting on the falling magnet is negligible, which feeds into the assumption we made that gravity and magnetic force are the only two forces acting on the falling magnet. For the experiment itself, the system was the aluminum tube, and the magnet and the surroundings was everything else in the room. Here's the procedure. Here's my measurements and data. All the important measurements for the tube and for the magnet are shown to the right. I'm in the left. And then the times for each trial are shown in the table on the right, with the average being calculated at the bottom. For the checkpoint questions, why can't we use da da da? This is because the ferrous tube contains iron, and iron contains magnetic properties, so that it would basically interfere with the following magnet, thus skewing our data. For the next question, the magnet falls through the aluminum tube slower than it would in free space, as there's an upward magnetic force acting on it due to the induced current in the aluminum tube. For the computational model, we use GlowScript. As you can see, we first initialized all of our important physical constants as well as the graph. Here we created a bar magnet and created an aluminum tube, and in the other one we created a function for the magnetic flux created by the bar magnet. We then calculated the gravitational force on the magnet and the magnetic flux on the ring due to the falling magnet. Here we calculated the net force was calculated by adding together gravitational force and the magnetic force using superposition, and the change of velocity and position of the magnet were calculated using Newton's second law, and a graph was used in order to demonstrate this change in velocity as a function of time. Here's a picture of it, of the magnet. Here are the graphs that were produced by the GlowScript model. As you can see, the graph on the right is the graph of velocity as a function of time using my mu value from lab 2. This was not the graph that I expected, and the time was much lower for it to fall through the tube than it had been experimentally. And so after playing around with the values a little bit, I came to a new value of 4.5, which created a much more accurate graph. For the questions related to the GlowScript model, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. So which color? From above, the red current corresponds to counterclockwise, and the blue current corresponds to clockwise. And I can know this using Lenz's law. For the next question, nothing much would happen. The magnet would still fall through more slowly than it would had there been no current. Just the direction of the current would flip to what we see now. For the next question, if there were both relatively close when I use the second mu value of 4.5. It could be made more accurate by either splitting the tube into more rings or by re-evaluating the magnetic dipole moment of the magnet and finding it again through experimental means in a more accurate manner. For the next question, the shape of the velocity versus time plot tells me that at the beginning the force is the gravitational force and the magnetic force on the magnet are unbalanced, as the velocity either increases or decreases. Then they are balanced or equal to each other, as the velocity does not change over the flag section in the middle of the graph. And then towards the end, and again, is the velocity increased. There are also unbalanced, with the gravitational force being greater than the magnetic force. For the discussion, there was likely no model discrepancies, as a magnet can very accurately model a magnetic dipole. For a potential source of error, considering air resistance likely was negligible over such a short distance of falling, the only source of error was likely human error when I was measuring the time that it took to fall through the tube, and possibly an incorrect value of mu due to error from lab 2. For this question, if this were the case, due to Ohm's law, the induced current in the aluminum tube would be much greater. This would thus create a much greater magnetic force on the magnet and possibly counteracting gravitational force altogether and preventing the magnet from falling. For the next question, if this were the case, the induced current in the tube would likely be less, as the now holes that are cut would disrupt the current, and the magnet would probably fall through the tube much quicker as a result of a lesser upwards magnetic force due to a lesser current. For the conclusion, this lab allowed me to gain a much more thorough understanding of Faraday's law and how it can be modeled in real life. This lab allows us to more deeply understand induced current and EMF resulting from changing magnetic flux. And this lab gave us experience in simulating an important physics theory using everyday objects. Thank you for watching.